And I'll say that over again. Hello, everybody. Happy New Year. It's top of the hour. We are moving to a 7 o'clock start because we always have too much to say and we always bump up against the custodial staff here. And that's a perfectly good thing. But then also there's lots of people have been saying, you know, evening sessions for other clubs starts at 7. So we're going to do this and do give feedback. I know some people means that you don't get your dinner hour or whatever. You know, we want to serve this community. So whatever works best, we'll do. And I know we'll never make it so that everybody can get everything they want, but we're going to try to optimize. Okay, so what I have right now are presentations by Reg and me, and rumors of a presentation by Dave Robinson.
Well, a photo.
A photo. Oh, good. From Edmonton.
Yeah.
Oh, we always love that.
Kind of had a hiatus for a while, but it's
that's good.
Hopefully he's back.
Yeah. So when we see Dave, that would be a good thing. And we've asked Dave Payne to talk about next week's speaker.
There is Dave now.
We still don't have. Hey, there's Dave. He's in person. And do you indeed have a picture from Edmonton?
Yes.
Okay, you're on my list then.
Get it to you.
We still have not got the go ahead to start university speakers. So we're going to keep speakers coming in on the Astro Cafe. And please put forward to Chris and me ideas for who we would like for speakers. I know that we've had a few ideas, but we didn't really push that a lot last term. I don't think we had anybody December, November. Anyway, let us please start with Reg's Galactic Mystery.
Oh. This is Reg's hand. For various reasons, I've been kept off the screen. So it might be a benefit not to have me there.
We can fix that.
Don't you never say stuff like that or
Turn the whole screen.
Yeah, you can turn. There you go.
Hey.
That is me.
Hey, good.
Well, Happy New Year, everybody. Just going to share the screen.
Progress.
And here we are.
Somebody has a speaker on.
We're getting a bit of.
I think Dave's maybe.
No.
Where is it? Clear enough?
No, there's an still.
Okay. We're getting audio feedback.
Without even trying.
Yeah.
Yeah.
I think Dave Robinson's audio is on.
No, it's like no, I turned it off. You mute your microphone, Dave. Yeah. There. Now I think it's gone. Yeah, thank you.
All right.
Okay.
Okay, before I get going here, I'd like to remind people of a resource that we have here, but on the
Cookies.
Besides Viva Pups, we have something else that is offered by the Victoria Center. But on December 6th, I thoroughly enjoyed a wonderful presentation given by Ron Fisher It was a contagiously enthusiastic presentation on his adventures with astrophotography. And although he employed the word easy, the photo of his setup framed the complexity. And here is the mad array of wires and all sorts of little devices there. And it also minimized the magnitude of his remarkable achievement because Ron amazed us all with how, one, is quick of progress, and two, the wonderful images he had, and three, his wonderful enthusiasm for this. So Ron, thanks so much for sharing that. But I just wanted to bring this up. But perhaps you, like Ron, would like to give astrophotography a try. But we're intimidated by this complexity that Ron let out of the bag, but did not have a good site, and you do not have the funds. But there's good news for Victoria Centre rascals. It's called the Victoria Centre Observatory, or the VCO. For people who are new to us, we always talk in acronyms, so the VCO. And astrophotography is possible with some speed bumps removed. So let me explain. And this is reopening real soon. Maybe people are aware that they're doing construction and road repairs on the hill up to the observatory. And I just got a message from Derek Mann about an hour ago. The snow and holidays has slowed down the progress and reveals that that road will be open in the early to mid-February period, when we can then go back up to the PCO. But that's the latest we have now. And this is a Victoria Centre Observatory. The door on the right is the home for our 20-inch Obsession Dobsonian, and a lovely 12-inch Dobsonian as well, for people who don't like to scale ladders if they're looking up at the zenith area. To the left is the area where this roof slides off, and we have our telescopes in it. And since the pandemic, very few people have been up there. And when we last had the VCO open before the restrictions came in, we had a 16-inch Ritchie Krejcian that has a defect, and it was sent back to the factory. They could not fix it, so they gave us a store refund at OPT. In the meantime, we have acquired a 12.5-inch OGS reflector. It's a Schmidt, a Ritchie Krejcian reshaped grade reflector, and 5-inch Takahashi refractor that we acquired around 2020. And this is the first light with it. I slapped the camera on the back and took a picture of that area there and verified that it indeed does work. So that was encouraging. I just want to give you a show of this refractor. Can be easily swapped between visual and photographic use. And so you just could put a diagonal on here in your eyepieces, your way to go. Or else you can put on, in this case, we put on a specialized reducer and field flattener that you can slap your digital digital single lens reflex camera, a Canon type, onto the back of that, and you're all ready to take pictures with your own camera. And it would take just seconds to set that up, and then we're away to business. And the next picture will show this is what my camera is, which is a modest Canon Rebel. It's called a T3i, but we're trying to discourage part numbers here. At any rate, this can take pretty nice pictures with it. It's not a modified camera like Ron's was, and so it will not show. A camera like this would not show the hydrogen alpha bright reds that some of the other cameras can pick up. But still, it's pretty good. And if you have one of these things sitting around, you'd have a lot of fun. If you came up to the hill, put that on, and started bagging photons. This is another thing that we have added on to the back of the Ritchie Craigyan 12.5-inch reflector. And as you can see, the optical train is rather elaborate. And so it is not that friendly to swap that out and put in your camera on the back of that one. So for now, what we have here is a 61 megapixel cool monochromatic camera made by QH1. We have a filter wheel. We have an off-axis guide here, and we have a thing that's unique with this reflector, an autofocuser, which does the autofocusing by moving the secondary mirror back and forward, and that is controlled by the software in our software system called SkyX. And that's enough complexity to scare most people away, but I just thought I'd show up for completeness. So this is a picture that I took with a 5-inch refractor a couple of years ago, but it shows you the capacity of what you could do with a modest camera like mine. And the reason that I'm showing this is with Andromeda. And Andromeda is 152,000 light years across. And it's 2.5 million light years away from the center. So that means the back edge of the galaxy is 2.6 million light years away. And because of that, it is quite a long ways away, but it's our closest big galaxy. The Triangulum is 2.7 million light years away. That's the next big one we have close to it. But if you, somebody calculated the mass of this, and it has the equivalent of 1 trillion solar masses. So roughly 1 trillion stars in this galaxy. Well, just think about it. That's a million stars. So when you think about that and do the math, Andromeda must be teeming with amateur astronomers. And I'm sure that they have Schmidt-Cassegrains and reflecting telescopes. And no doubt their favorite target is the Milky Way. So they're probably looking at us every night and taking pictures and showing them to their own friends at their own Astro Cafes. But the breaking news is 2.6 million years ago, Earth entered a plume of a nearby supernova. So as we speak, light from this supernova is just arriving at the far side of Andromeda. So those far side amateurs are busy photographing our neighborhood of the Milky Way. So just think about it. So we're a hot topic right now. Now, wait a second. How can you say a supernova exploded in our neighborhood 2.6 million years ago? Well, that's what this presentation is all about. It involves a smoking gun, in this case, actually the plume of a supernova, the remnants of the supernova. Possible damages to the Earth will be discussed. And there's a star hunt. Where did this culprit go? So these are all the ingredients of an astronomical mystery. And so this is the case of a close encounter. So first of all, smoking gun and damages done. In a 2016 paper that was published, it absolutely amazed me. I kind of get drawn into these black holes all the time. And I wrote an article in the October 2016 Sky News about this, and there's the link to it. All of our Sky Newses are available on our Victoria.RASC website. And a former UVic grad student was one of the lead authors. His name was Sean Bishop. He went and got a graduate degree at UVic, and then he got his PhD at Simon Fraser, and then he went to work for the Max Planck Institute in Germany. And they had an extremely sensitive mass spectrograph that could detect 1 part in 1 trillion. The word trillion keeps coming up here on this thing. At any rate, this paper absolutely captivated me, and I went down a rabbit hole, as I often do in these cases. And the link to the paper is here. And in addition to providing proof of a nearby supernova, it suggests that this event coincided with the Pleistocene boundary extinction. So it may have the radiation from the supernova might have impacted life on Earth. So the plot thickens. At any rate, I was planning to do this for a long time, do this presentation, and I've been consistently rewarded by procrastinating. So I was going to present the gory details of this paper when last month I learned of a wonderful presentation by Dr. Derek Muller. Derek grew up in West Vancouver. He got his degree in engineering physics at I think it was Queen's University, and then he went down to Australia, and he's got a PhD in communicating physics through electronic means, and he just did it in a time just before everything started to really develop strongly with sharing all sorts of information. So I'm going to show you this video, and it's going to take 18 minutes. And I've got another part for another night, the hunt for the culprit, and my quest to find a current location for a supernova. I was really looking into it. I actually took audited a course at UVic to learn more about this. And then all of a sudden, magically, last January, Catherine Zucker and others published the very paper I was looking for. So those who, life rewards those who are patient and don't do anything right off the bat. At any rate, so if people are interested, and I'll revisit this one next, but for now, I'm going to go on and do the, set this up. And so what I'll try and do now. So this guy is obviously a remarkable feature. Science communicator, and he's got a YouTube channel out here. This has been only out for a month, and he's already had 13 million of subscribers or viewers to this thing. So it's very popular, and I learned a lot from that video. And he expressed almost absolutely everything that I wanted to tell you about that first paper or two. The one thing that he didn't mention was we to find out this iron 60, we have to thank a microorganism that had an appetite for iron, and it basically ate the iron up and sequestered it, and it allowed the iron to be in enough quantity that we could actually measure it accurately enough. And this was a critical thing for these scientists in Germany to use their spectrograph, mass spectroscope to detect the minute quantities of iron 60. At any rate, if there's interest, I'll follow up with, well, they think where the roughly what part of the sky that supernova is now after it passed by us. And it's another story that takes advantage of the Gaia data that gives us more accurate measurements of the speed and distances and location of all of the stars in the sky near us, as well as calculating a thing called the atmospheric extinction, which allows us to determine if there's a super bubble versus more densely populated space. So at any rate, I'm gonna, that's enough for me now. Thanks for your attention, and I'll turn it back to the team. There you go.
Well, thank you, Reg.
That was great.
Going to move this here. Am I in the screen?
Well, we could nudge it a little.
Where am I?
maybe. You're on the edge still.
Okay, so that was super, and absolutely, you were invited to continue
Please do.
and tell us what goes on after that.
Okay, I'll let your thoughts be compressed and absorb it, and I'll come back in a month or so.
Okay, good.
How's that?
Well, that's a very good way to continue on with Dave Payne saying, since we don't get to have Rich give the talk next week, but we do have a distinguished speaker.
Yes,
You're on,
we
Dave.
do. I'm getting an echo. Our speaker next week will be Laurie Rousseau-Nepton, who hails from Quebec. She was actually the first Indigenous woman to get an astrophysics PhD in Canada. She's working at currently the Canada, France, Hawaii telescope. And of particular interest to me, but hopefully to everyone, she's been studying hydrogen star forming regions and the makeup of the gases other than hydrogen that are in these areas. If I could just share my screen for just a second. Is everyone seeing that? She has a web page that I visited. The contact was actually made by Margie at first, and she passed this contact on to me. But she's using something called Cytal, which is very interesting. It basically takes an image of a hydrogen region and provides the entire spectrum through some voodoo magic, which I don't quite understand. It provides the entire spectrum of each pixel. So what we poor astrophotographers have been going around with our three filters trying to detect hydrogen and oxygen and sulfur. This gives you the entire composition of the gases in a star forming region with one image, so to speak. Should be really interesting to talk about how stars form and what's going on in these star forming regions. Now, 90% of the stars have that are going to be formed have already formed. So this is probably the major place of stars forming in these hydrogen elements going forward. So it's pretty exciting. Hope you can all join us.
That's great. And as we do have a special speaker, we won't plan on anything other than some news items for next week's Astro Cafe. So start thinking about what you'll do a couple of weeks hence. Okay, so why don't we have Dave show off his regular issue of RASC Edmonton in all their glory.
And Dave, can you stop your share?
Yeah.
Thanks.
Thanks for the reminder.
Another Dave start his share.
And then I'll give my talk.
See if that will work.
I need to find it.
Okay, there we go.
Ooh,
So this is a photograph by Abdul Anwar, who used to be was a longtime member of Edmonton Center. He moved to Cochrane, not 20 miles west of Calgary, not too long ago. And we've shown pictures that Anwar has done before. This one is noticeable because it won the Sky News Picture of the Week Award for December the 10th to 16th. And so what we have here is it's called WR134. And WR134 is a variable Wolf-Rayet star about 6,000 light years away from us. And the faint blue and red nebula surrounds the star, and it forms a very faint bubble due to the intense radiation and the fast wind from the star. He says that the nebula is about 5 times, the star that created the nebula is about 5 times the diameter of the sun and much hotter at 60,000 degrees Kelvin. And that makes it about 400,000 times brighter than the sun itself. So it's a very bright star. Anwar spent a few days between October 6th and November 5th taking 33.5 hours of data. And he managed to combine them into this photograph. It was difficult to do because trying to balance the O3 with other signals to have the bubble show up against the background hydrogen alpha. He uses a Celestron C11 Edge HE telescope with an ASI 1600 millimeter pro camera and a ZWO filter reel. So some of the material that we have on our own scope here, actually. So that's his image taken from Cochrane.
We can't get 33 hours of clear skies.
Well, Calgary, you can get, picking up over after night, you get Chinook conditions that will sometimes do that, right? So,
is that the sort of picture that you know that it's going to work ahead of time, or is it you have to do the 33 hours and then you see whether it's going to be okay?
I think he does it in sequences, right? And then he'll take a look and see if anything's going to come up. But I think pretty much he took this data over several nights. So he may have done some pre-processing, but he's very skilled astrophotographer.
He's really come a long way in the couple of years he started showing those.
Oh yeah, it's
great to see.
So that should have stopped sharing there.
It did.
Well, great. I'm curious because Dave is quite far from the microphone for the people out in Webland. Can you hear okay when somebody's speaking further at the back? I am so pleased. That's very good. We have just this one little microphone in front of us and it's doing a great job. Okay, now it is my turn. And let's just get the share going and get the presentation going. And we had Reg give his fancy title, so I decided to make a fancy title too. So sunrise, sunset, and the path of the sun. And this was motivated by our friend Margie, who did you write this to everybody or did it go just to Dave and me?
Just to you, just to the two of you.
Okay, I wasn't sure whether you were just broadcasting that you had this interest and you thought, hey, maybe Randy could do this. Anyway, it is a topic that is near and dear to me because I actually use the sun in an interesting way when I do my field work. But it helped me this weekend doing the research for it. I finally understood something that I've been using for 30 years, but never, I just knew that it was out there, but I didn't really understand it. On the other hand, I tried explaining it to my carpool mate on the way home, and it was tricky. So let's see where this goes. So what Margie wrote, I need a bit of input about the info below. If the sun is now setting, this is in December 8th, she wrote, if the sun is setting a bit later each day, how is it that the longest night is December 21? Wouldn't the longest night have to be on December 6th? Okay, so, and the answer is the discrepancies arise from the tilt of Earth's axis and the ellipticity of Earth's orbit. So let's go into a deeper dive. So start off with, is Margie right? And so I went to time and dates and downloaded the December and January sunrises and sunsets. And you see, we also have over here solar noon. That's an important part of the puzzle. And you graph them up. So we have the date from December 1st right till the end of January, and then the time from 7 in the morning till what is that, 8 o'clock at night. And sure enough, the sunset has its minimum. The earliest sunset is somewhere around December 8th. It's pretty flat there, so it's and the table only was to the minute, so I'm not sure exactly what day, but somewhere there, plus or minus a couple of days. And the latest sunset is around January 1st. And we've all been told a million times that December 21 is the shortest day. And you can see that the red and black lines are closest to each other. So here's exactly the same graph, but I've subtracted 4 hours from sunset and added 4 hours to the sunrise, so that you can, it exaggerates the things a bit. And you can see that the shortest day is indeed between the earliest sunset and the latest sunrise. And really, it's because at the same time, we're not looking at the sunrise and sunset with respect to solar noon, but to civil noon. Okay, we live in a society that doesn't want to live by the sundial. So you take the year and you divide it by so many seconds, and you do an average day. So the actual day can be up to plus or minus 30 seconds around what is the duration of the real day, meaning from solar noon to solar noon. And at this time of year, the days are, let's get it right, the days are longer and the noon is getting later. Hold on to that thought. Let's see as we go through this. Okay, so let's just remind everybody, I hope you learned this at some point, that the Earth's axis of spin, so the line that goes through the North and South poles, is tilted with respect to the plane of our orbit around the sun, otherwise called the ecliptic. And at the autumn and spring equinoxes, the let's word this a different way. The equator crosses the ecliptic, and that the sun is right on the equator at the equinox. It's called equinox because we have 12-hour day, 12-hour night. Whereas at the summer solstice, the sun is at its highest latitude or declination, using the astronomical word. The sun lies over the, a latitude of somewhere in Mexico. In the winter, the sun is over a latitude somewhere in Chile. And so that is the main cause for the seasons, but it's also going to affect the length of day. So let's first of all talk about the effect of the declination or the latitude of the sun on the number of hours of daylight. So here we are, you're standing in the middle of this circle, pointing south. And we're now around that blue line, that December 22nd line. And you can see without much difficulty that the sun goes around the Earth in 24 hours, 15 degrees an hour. 15 times 24 is 360 degrees. That doesn't change. The Earth is a very good clock. And when we talk about the sun moving, in fact, it's the Earth spinning around the sun, saying stationary, but we can pretend for a while that it's the sun going around the Earth. And you can see that it's just not got as far to go in that blue line as it does when the declination is really high. Then it goes from way in the northeast at 5 a.m. and it goes at noon. Noon is always going to be where the sun is highest and is south when we're in the northern hemisphere. And then it will set way up in the northwest. So if you have a north window, you still get to see the sun in the summer. The sun has a longer path to go and a shorter path around on the nighttime, on the other side of our horizon. Whereas in the winter, it's the opposite. And so when we say that the shortest day is on December 21st, it's because the declination or the latitude of the sun is lowest on December 21st. The higher the sun's declination, the longer the daytime. Now, I say the daytime because I'm also interested in what is the length of the day, because that's why the local noon is going to go forward and back in time. Okay, so that's the second part of Margie's question. The shortest day time, the shortest time when the sun is above the horizon, is indeed on December 21st. But it is not the date of latest sunrise and earliest sunset, because local noon is changing every day through this season. And so that offsets those two other things. So this is just another way of showing it. So here is a picture of the day, a nice day point in time when the sun is over someplace in Chile. This is the winter, and you can see that the sun is directly overhead Chile, and that vertical line that is lit is not aligned with the north-south pole of the Earth. It is tilted by 23 degrees. Okay, I think I've pushed that point enough. Is everybody happy so far? Good. So we've talked about the length of daytime, but what is the length of day? So let's consider about this. There is actually more than one day. The sidereal day is how long it takes for the Earth to spin around on its axis 360 degrees. And so if you look at the distant stars, one day to the next is 23 hours, 56 minutes, and 4 seconds. Okay, and that's every day of the year. That's how long it takes for the Earth to spin 360 degrees. But during that one day, the Earth goes around the sun another degree. Not exactly, there's 365 days in the year, 360 days in the circle, 360 degrees in the circle, but let's just call it 1 degree for making it easy. So every day, solar day, or what's called a synodic day, a synod in the church is when people gather together. And so a synodic day is when the Earth gathers with the sun, but you can also call it the solar day, is on average 24 hours or 86,400 seconds. That's an average. But in fact, it can be minus something like 22 seconds or plus 34 seconds. That's how much it varies over the year. And my question is now, why? Okay, another picture of the same thing. So we start with, here is yesterday. Here is one sidereal day later. If you've ever been in an observatory that has sidereal time, you'll see that those seconds go a bit faster because those days are a bit shorter. They're 4 minutes shorter. And then what happens is we then have to add a bit of time to get the sun pointing south and overhead at noon. Okay. So we're going to talk about two things. We're going to talk about the obliquity and the eccentricity. The obliquity is that 23 degrees, that the difference between the ecliptic and the equator. And this is part that I have to tell you, I've been using the equation of time for my whole career as a paleomagnetist. And it's just this weekend that I finally got into my thick skull how this works. And there are very few websites that talk about it. The Wikipedia has a paragraph which makes absolutely no sense to me. And so let's see if I can explain this to you. Okay, and we're only going to look at the equinoxes and the solstice. So let's say that the Earth's orbit is circular. Forget that there's a perihelion and an aphelion. The Earth is always the same distance from the sun. And what that means is that, and not only is the motion circular, but we also, following Kepler's third law, the speed of the Earth going around the sun, or this is a geocentric view here, so of the sun going around the Earth, is uniform. So let's say also the Earth is a bit closer in, so it takes 360 days for the year. So 1 degree every single day. Doesn't matter whether it's an equinox or a solstice, the Earth every day is going to move 1 degree around this circle. But we don't measure time by the latitude or the declination of the sun. We only measure it by the longitude. Okay, so what we're always interested in is how far does the Earth have to turn to get back aligned with the sun at noon? How long does it take to do the 360 degrees for the sidereal day, and then that little bit more in longitude to line up the Earth with the sun. And so what you see is when we're at the winter solstice, so around now, the orbit of the sun is pretty well all in longitude. There's no change in latitude during the winter solstice or the summer solstice. All the motion is in longitude. Do you see that? And so that means that that whole degree of rotation of the sun around the earth around the sun, I don't care whether you're geocentric or not, but all of that motion is longitudinal, and therefore, while it does the 1 degree on that red circle, it's all, every second of that is going to have to be converted into extra rotation. So the days are longer during the solstices, whereas at the equinoxes, there's still a change in longitude, but there's also some latitude change. Okay, it's the same distance of arc, but it's not the same projection onto the equator. What did I write on my next? Yeah, so we have only longitudinal variation from day to day at the solstices, but we have longitude and latitude at the equinoxes. And so when you project the position of the sun onto the celestial equator, there's less difference per day, and those days are going to be shorter. Does that make sense?
Yeah.
You can see why they never tell you about this in the quick version, because it is not easy. But I think I understand it. So I hope that I've explained it to you in a way that makes sense. Okay, so that accounts for about plus or minus 8 minutes of the length of day throughout the year. And then the other one is the eccentricity. And this one I've always understood, or at least for as long as I've paid attention to Kepler's laws. So in fact, the Earth's orbit is an ellipse. So the 3 laws of orbital motion that Kepler figured out, first one is that the Earth orbits the sun on a plane through the center of the sun, or the center of gravity of the whole system. It's on a plane. Second, the path is an ellipse with the sun at one of the focuses. And the third law is that the amount of area swept by, in this case, a satellite around the Earth or the Earth around the sun, the amount of area swept by the planet is a constant. This is the most tricky. Oh, it's second law, not the third law, whatever. This is the trickiest of Kepler's laws, but it is absolutely essential to working out how to get a Artemis to the moon. You play around with these perigees and apogees, and anyway, it's called a perihelion when we're talking about the distance from the sun. The Earth's perihelion, surprisingly, is not when our summer is happening, when it's nice and warm. The Earth's perihelion is around January 4th. We just passed it. That is when there's more solar radiation hitting the Earth than at the aphelion, which happens in July. Bizarre, but that's a fact. It works for the southern hemisphere, but not for the north. Anyway, so when the Earth is close to the sun, then it travels further, it travels faster, and again, the longitude that is covered during one day near perihelion, so in the winter, it takes longer for the Earth to catch up to noon. You've got the 360 degrees of sidereal day, and then that extra little bit, 4 minutes and some. So the days are longer in the Northern Hemisphere winter, and they're shorter in the Northern Hemisphere summer because we're at aphelion. And so the Earth does not go as far around the sun. And so that extra little bit above sidereal day is shorter. So we have the eccentricity. The eccentricity makes a single wave per year. Okay, so the days are shorter in the winter and they are longer in the summer. And the obliquity, the tilt of the ecliptic to the equator, you get 2 waves per year. And you put those together, you add them together, and you get the equation of time. And what that says is that the Earth varies by plus or minus 15 minutes. If you set up your sundial, it's going to be, it's going to change by half an hour between its fastest and its slowest. Okay, and that's just the way the Earth works. And then on the right is the analemma. Oh, I was going to look up why it's called analemma. While I do this, can somebody Google it? I'm sure there's a good Greek etymology for it. Anyway, what you see with the analemma, the vertical is the declination or the latitude over which the sun is rotating. So equinox down there, we're at the winter, equinox, summer. And the horizontal is the number of minutes your sundial is going to lead or lag the mean civil time. So it is very often put on globes. I think a lot of people look at that and say, what the hell are they doing there? But it actually makes sense. Another thing, which is really cool, which I learned this weekend, is you can actually draw the analemma on a globe. This would be a great amateur. Oh, it's a pedestal of a sundial. Oh, isn't that lovely? Thank you, David. You can set up a globe on a sunny place. You set up the longitude for where you live, and then you can see where the sun is directly over the globe with a cute little apparatus that you can make with just a little plastic cup and a crosshair. And I think I'll see whether I can play a game like this someday. But you can, in your driveway, you can plot where the sun is over the globe by going out at noon every day and seeing over what part of the globe you're actually where the sun lies. I think it sounds like a really cool project to do. Another famous way that you can see the analemma is to photograph the sun every day at noon, or I don't know how many pictures. This looks like about once a week. This was done in Greece, where there's lots of sun. That's a good place to do it. It would be harder to do here, although Luca seems to do things like this in Edmonton.
Takes him a while.
Yeah.
A couple of years sometimes.
That would also be a really fun project to do. And in fact, I did it. This was my early COVID project, if you guys remember. This was June of 2020, and I reported it in the September Astro Cafe, one of the earliest ones. But for about 50 minutes before and after 1:30 every day for about a month, I plotted where the shadow of the sun plotted. And so each one of those curves is an analemma, but just the tip around the summer solstice. And that was a really fun project. Took way too much time, but there you go. You have to suffer to have fun. Okay, and then the last thing for the people who are here, I actually have a sun compass, but I use this for my work. Let's first of all put it here and then I'll pass it around. Okay, so what you see here, can you see my picture? So it's basically a backwards sundial. So normally, I'll pass this around the room here. Normally with a sundial, what you do is you know which way is north, and you look at the shadow to tell you what time it is. Whereas what I do in the field is I set my watch for local solar time, and then I turn that dial around until it says the right time, and then I know which way is north. And it's really good if I'm trying to find the direction of a highly magnetic rock, because my compass, my normal magnetic compass, can give any direction, but this one will always be right. So in order to do that, I have to know what is local solar time. So that is civil time. And then there's a longitude correction. So we're in Pacific time. So that's based on 120 degrees west. We're more at 125 here. So it takes about 20 minutes for the sun to get from Pacific reference longitude to our local longitude. And then I have to put in the equation of time. So, you know, I just look this up and I read off how much I have to correct it. And then, because I usually do my field work in the summer, I have to put in an extra hour for daylight saving time. So our local time, our local noon around here in the summer is more around 1:30, 1:20, 1:30, somewhere around there. Okay. And that's it. I hope that was clear.
Thanks, Randy. It was great.
And
Well-
thanks, Margie, for getting me going.
Well, that explains why I didn't understand it.
Well, I think Margie made the lemma, which is the standard argument, saying that December 6th was the earliest sunset. But you made the analemma, which is up against the lemma. So
Thank
that's
you
what
very
I
much.
figure. That's what I posit is the origin of analemma.
There you go.
That's just made up, of course, but.
Oh.
So Randy, did they have this all completely down pat
Oh,
thousands of years ago?
Babylonians were
Yeah,
excellent
yeah.
at this.
Okay.
Oh, absolutely.
Was back to sticking the
Stick in the sand. Yeah.
marking.
I mean, it's interesting because measuring time back there, they figured they had to use water clocks and things.
Yeah.
To get a standard second. But because there's all sorts of cultures that divided day into 12 hours and divided night into 12 hours. And that was, you know, and they were flexible about it. And, you know, most people back then actually cared about the day because they didn't have lights. We're the weird ones for decoupling ourselves from the astronomy.
We're sitting here in the dark right now.
Oh, it's crazy. We should be out there looking at the stars.
So when you calculate local solar time, you use the calculation. But you could also determine it by sighting the sun, and when it reaches its zenith and starts to drop, that's noon.
Absolutely. So
Yeah.
I've done that with my sextant.
Yeah, okay.
What you do, I mean, and this is any navigator knows the sort of thing, that noon is the time that the sun is at its highest. What's interesting is because the sun is horizontal there, you can't actually do it at noon. You have to do a few measurements before noon and a few measurements after noon. And then you fit a parabola to that.
Yeah,
But I've done that, and it's a really fun exercise
it's
to do.
accurate.
Oh, I was accurate to I think it was about 5 seconds doing that.
Try to do it from the deck of a pitching
Yeah.
shaft.
That's different. Can you do that? Are you a navigator?
No, but you can do that.
Oh, of course. I mean,
I've never done it, but
no, I just go to Dallas Road and sit on the bench. This is a really good COVID exercise when you're just stuck there and you don't have anything that you can do.
Well, there's that movie called Master and Commander.
Oh, yeah.
And the midshipmen are learning how to navigate. And Russell Crowe says, call noon. And they've all got their sextants pointed at the sun. And that's how they determine noon. So you can calculate
Oh, that's great.
your local time, but you can't, unless you've got the time at Greenwich, you don't know where the hell you are anyways.
Yeah. So you take very good care of your sextant. And I have my sextant is a 1941 World War II. It was deployed on one of the Canadian Navy ships. And it's in great shape. And in December, I slipped down my steps on some ice. And I didn't hurt any of the actual measurement parts, but I did hurt this light thing on it. And I'm really irritated because this beautiful instrument has survived till now so beautifully. And I slipped on the steps and broke a piece of it.
But calling noon allows you to set accurately latitude,
Yeah.
and that's what longitude is a whole different deal.
Yeah.
Yeah.
There we are.
There's a movie called Longitude about
That's a great movie. Yeah.
about how you get a clock that works.
Thanks, friend.
Joe Tur, so that was on a real ship.
Yes.
Yes, that was on the Volendam in the South Pacific, and a junior officer was teaching a senior officer was teaching a junior officer how to shoot the sun at noon from the top deck.
Okay,
So
so
I was reassured because they had a backup system.
they have a sextant on all the Coast Guard research ships, and they had about 30 years where they stopped training celestial navigation, and they've just restarted recently. But it's the sort of thing they all kind of roll their eyes, say, "Oh, I had to do that in training a long time ago," but they don't like it. They
What
much
if you're
prefer
in-
to look at the GPS.
What if you're in a lifeboat?
Exactly.
Or in an airplane.
And you can imagine Shackleton trying to get back to
Oh my goodness!
civilization.
Yeah.
Doing that.
We had every 4 months, we have a group of new naval students who come up to the center,
Oh, good.
and they all have their sextants, and we take them into the planetarium, and we put the planetarium on as for the timing and where the sun,
You can do it in such a short little place. You can actually do.
Well, she's showing them how, like, the leader is showing them how they can do it. So they're sitting in the planetarium with their sextants and kind of working away on that. And they do, and it's really cool because they come all in their gorgeous uniforms and looking pretty darn sharp when they come in and do that. So so they come in, but every 4 months.
But you've got a good horizon there for them to
We
use.
have a
Yeah.
horizon, like we have the horizon in the planetarium, and then they can make it all.
Yeah, I tried to use the sextant in the Okanagan, and the problem there is finding a horizon.
Yeah.
And if you go to one end of Okanagan Lake and look as far as you can, the longest reach you can get pretty good, but it's still not
Yeah.
quite the horizon.
You need to climb a mountain.
Yeah.
Or do it from Regina.
Looking toward Moose Jaw, yeah. Wow.
Dude, have any of you taken Power Squadron?
Yes.
That's where you can learn celestial navigation.
So did everybody get a chance to look?
Yes, thank you.
Do we have any other, taught this topic in the Coast Guard. Good, thank you, Peter. Do we have any other topics?
A question,
Brian?
Randy. Yeah, no, that diagram that you had with the declination at summer solstice and winter, you had the sun was appearing, or like the sunrise and the sunset were at the same, is it azimuth?
Well,
On those days, is that correct? Because some of my hours I noticed that this, the sun will come up further north and then sets further south, or vice versa. It's not a rising and setting.
not sure what picture you're talking about, so let's.
Yeah.
You're at the end, so you go back.
It's towards.
But yeah, that was fascinating to, about the change of the speed of this Earth around the sun there as well.
Okay, so what slide are we looking for?
Yeah, 8 or 9. 8 or 9. So you see the sunrise and the sunset for the blue and the red lines are, they're at, is it the same? Is it the azimuth or?
Okay, yeah, so that's, yeah, in the winter, the sun sets in the southwest, and in the summer, the sun sets in the northwest.
Correct.
So,
and on those days, they are at this, and what is that, at that angle called? Is that the azimuth?
oh, what would you call that? Yeah, that would be the sunset azimuth, yeah.
Azimuth. So they're the same on those days, but I've observed where the azimuth, the sunrise and the azimuth are, sorry, the sunrise and the sunsets are different azimuths. Like they're not opposite each other for most of the.
Okay, I just want to take a look at this table.
So maybe just on those 2 days, the sunrise and the sunset are at the same opposite, like the same azimuth, but
The
opposite.
sunrise, it says, is 123 and 237. So 237 is 57 degrees beyond 180. And yeah, 57 degrees before 180. So yeah, those are symmetrical.
Symmetrical, yeah.
Those are both 57 degrees from 180 on December 1st. So Brian, if you don't see that they're the same, I'm wondering, what are you using for south? Like,
Well, I'm just thinking, I was trying to, also on those days, it looks like the azimuths are symmetrical, but in between them, we're probably seeing some, or do we observe some shift north or south for one or the other?
well, yeah, you can see that as we go from December 1st to 11th, the sun is rising first at 123, later at 124, then at 125. It's going further and further towards the south every 3 or 4 days, and it will actually turn around on the solstice.
Mm-hmm.
So now the sun will be rising further and further north until it actually will be rising in the east everywhere on Earth on March 21st.
Yeah. Okay, I'll look at those a little closer there. That's helpful. Thank you.
this is really fundamental astronomy. So
Mhm.
sort of thing that I hope that amateur astronomers are interested in, because it really, you know, when you start looking at these planetary systems happening around other stars, or you're looking at how galaxies rotate around each other, it's all Newton's gravitational law, Kepler's laws of orbital motion. It's
Mhm.
really beautiful.
Yeah. The other thing that I've come to understand is, because I was grew up think, in the wintertime the Earth is tipping towards the sun. It's tipping, but the axis of the Earth is, used to say, 23 degrees or so
Yeah.
off. But that remains the same the whole way around in the ecliptic.
So there are three numbers: the eccentricity, the obliquity. Can anybody remember the third parameter? Anyway, these vary over periods
Mhm.
of tens of thousands of years.
Yeah.
And they I don't remember which one is which, but
Mhm.
there are these cycles. They're called the Milankovitch cycles, and they directly affect the Earth's climate.
Mhm.
You can actually see in the record of the ice ages. It's interesting because you go back about 800,000 years, there's an ice age every 100,000 years. When you go older than that, then it's about every 30,000 years. And you see it in the oxygen isotope record, and you see it in the sea level records, and but it is completely driven by the amount of insolation which is affected by these three orbital parameters:
Mhm.
eccentricity, obliquity,
Precession.
the precession. Right. So that is,
And then.
right now we have
40,000.
Polaris is our North Star, but it moves around.
So that's the 23 degrees.
Yeah, no, yeah, the tilt, 23.
The tilt is the obliquity.
If you're
Oh.
going Polaris or point,
And that
North
goes-
Pole moves around in a circle about every 26,000
Yeah,
years.
traces an arc
Yeah.
through the sky.
Do you guys want me to give a talk about the Milankovitch cycle someday?
Sure. Mhm.
A while from now, but it's a really hot topic. It's really important for understanding the Earth climate.
Sometimes it's hot, and sometimes it's cold.
There you go.
That's my level of understanding. No, your talk has raised a lot of conversation, a lot of discussion, which is good.
And if you don't understand everything, it's okay. I was really keen that people kind of know that these are the sorts of things you can do with very simple measurements. So simple, I can make them. And it's kind of fun to understand this universe we live in using.
And it gives you an appreciation for the sophistication of ancient astronomy.
Oh my goodness, yes. Shall we close David Lee with some SIG news?
Yeah, I don't know if there's much to say. The beginners group, you actually answered a long-standing question from the beginners group, so that's great. You did that tonight, so thank you. I think the beginners group, we're kind of going back to basics. So we were exploring constellations for close to a year, and now I thought it would be good. We have some new members, so we thought we'd go back to basics, like talk about what the different kinds of magnitudes are. And I think in the coming months, I was hoping to go through naming standards for catalogs, because it's often very confusing that we have multiple references to the same object. So I thought I'd go through different kinds of catalogs, how things are named. Comets are kind of interesting in terms of how they're named. And one of the most complex cataloging naming things I've ever seen is the ones that we use for variable stars, because they can be quite cryptic when you first see them. But once you see them a lot, then you can say, oh, I understand how that works. So yeah, so we're going to be doing things like that. I'm hoping we're hoping we're going to have some demonstration things like last year I took some people through the observation of Algol, which is a really easy variable star to observe, and I think we'll probably do the same thing. We'll do some kind of easy, kind of visual variable star things to get people started. So that's a beginners group. I've kind of started to exit the electronic assisted astronomy group because there doesn't seem to be a lot of activity there. But it doesn't mean that we're going to slow down our activity on SIGs. I'm going to sort of start to grow the citizen science one. So hoping to give a talk on that in the coming weeks on Cafe. And then we're going to start a citizen science SIG. And hopefully we will, as a center, maybe do some observations together. And I think that would be kind of interesting to do. David, do you want to say anything about the astrophotography group? We're kind of going like big guns there.
Yeah, we actually had a meeting just between Christmas and New Year. I can't remember the exact date, but so hopefully in 2 weeks we'll have a little bit to say. Just our monthly report from the astrophotography sake, but not a huge amount of activity for obvious reasons of late. But
okay, well, that's great. Yeah, so yeah, you're doing a great job, Dave. I think we certainly have kind of a core group of people that are quite interested in imaging, and obviously the thing that we have to live by is our weather. So the last group is actually the makers group, and I've actually started building some things over Christmas. I've started building what I'm calling my environmental box. I was kind of inspired by Pegasus Systems kind of do-all kind of environment box. It's a very small package that gives you data like accurate time, temperature, humidity, and they even have a cloud detection circuit. So I've tried to mimic that. So I've started building this box that does that. So I'm going to start off simple. So I've been kind of working with a number of sensors, but I realize now it's not as simple as that. Sensors have these little quirks, and there's a lot of software behind the sensors as well, even though there are sort of like sample scripts that are available on the net. They each require kind of tweaking. So I've already started my new rabbit hole. So if you want to see what's going on in that vein, join the makers group or just drop in. So I think that's about it. I don't know if anybody has any questions, but let me know if you're interested in any of those things. They're quite fun. I know there's some core people that attend each of those SIGs, but you certainly don't be afraid to join. Like the makers group is really not filled with people that are extremely experts in the area. I'm certainly not. I'm kind of one of these kind of people that just chance on something. I want to do something, and then I start bumping my way through it. So you can kind of watch me bump my way through it, or you can join me in my adventures.
When's the next beginner SIG, Dave?
The beginner SIGs are the first Tuesday of every month. They kind of sneak up on you, or they've been sneaking up on me. So we had one right after New Year's. So the next one is the first Tuesday in February. If you want to be notified of that, just make sure you let me know, and then I will add you to the distribution list.
Okay, thank you.
I was going to say, did you want to mention the bylaws?
Yeah, I'll do a couple of president's announcements.
Yeah.
So we sent out the draft bylaws to everybody, and then I sent a reminder this weekend, and we have requested expressions of concern. You can give expressions of delight and pleasure all you like. We appreciate that, but in particular, we are hoping to make the center a little more governable with these new bylaws. And so to change them, we need to do a special general meeting, which will hold, well, depends whether we get enough agreement on how we're going to go forward after this feedback round. But the 15th, I recall, is the last day that we will be able to accept comments so that we can then put together a kind of frozen set of bylaws that we can vote on in a special general meeting. And then if that passes, then we will hold our annual general meeting under the new rules, not the old ones. It means it's a simpler election, fewer people. But the other side of this, and this is where our search committee chair comes in, is please, this is a wonderful community. I think we have a great sense of volunteerism on all our events and things. I can't tell you how much fun I personally am getting working with so many members of this group, but we do need some people stepping up for the executive. It's not a nothing job. There's effort involved, but it is very fulfilling to have it with this group. And I guess the greatest thing compared to most volunteer groups is we don't have to do fundraise. So we can just get on with doing our program. So please consider putting your name forward. We have up to 3 under the new rules, there'll be up to 3 members at large. And that's a great way to get into how this organization runs. And then we have the treasurer, secretary, president, vice presidents. Please say that you'd like to help. And even if you've done it in the past, come and say it again. We love you. Is that enough?
That was very good, Randy. You remind me of those people on Channel 9 doing the fundraising.
Operators are standing by. Please call in now.
I don't want your money. I want your
Time.
time.
Some of your time. Yeah.
And if you don't, it's also fine. You're still allowed to volunteer for all sorts of things. And we can run our outreach and our various wonderful programs. That's also okay. There. Is that it? Is that a wrap? Oh, Laurie.
I have got some handbooks that we bought to be able to be sold to interested members. So we have the handbooks that go along with the Explore the Universe with small telescopes. We have the Explore the Moon handbooks, and there's another one, and I can't remember what it is right now. Okay, and they're $10 a piece. So that if you'd like one of those, if you're going to be going thinking in the springtime that you'd like to start one of those programs, then I have a nice handbook for you that you can use. I have got calendars here for people that have been waiting. And I've got another couple. I have 2 or 3 that are available. Not a lot, they've mostly gone, but if you are interested in getting a calendar and I have not talked to you about that, then please let me know. But I think things are kind of wrapping up here for that. But please let me know if you want any of the handbooks, because I have those to give to you. Oh, to sell to you. We make no money. In fact, we're losing money, a few cents on the calendars this year, instead of trying to make them as $16.02 or something like that. We just kept the 15, so we're just going to.
Your dues going to a.
Yes, into the small ranges to get everybody in. But you're having a great deal, by the way. Yeah. Okay.
Margie has a question.
A quick question. Randy, you gave me the name Mallory Thorpe quite a number of months ago. Yes. And I've been looking her up on the internet, and there is not all that much information on her, about her. And I see that she spoke. Did she speak at the the Star Party last?
Yes,
At the Star Party, and she spoke at International Astronomy Day, but that does not mean she can't also speak to us, because she's awesome.
Okay.
Yeah, she's awesome. She's in Germany right now.
Okay. All right. And my other question about her was, did she speak at Astro Cafe within the last few years? Like, I don't remember her, but no. On the internet, on the web, it does say, it does mention her name in terms of 2021, but I don't recall her speaking, and I've been around for most of them. So
she spoke with the FDAO, so it could be that.
Okay.
We had her for one of the party. Yeah.
I can't get enough of her. I think it'd be just fine to have her with us.
All right. So what I will do is just I will get in contact with her, just in terms of information itself, so that I can do her as one of the women astronomers, and then at that point, then maybe we can ask her to speak.
Very good.
So she's just starting her program. She might be pretty busy now. She just landed in Germany in the last week or two, I think. So.
Be on a different time schedule.
But she's a very good speaker. Okay, everybody, we're going to schmooze here and call an end of the hybrid session, and we'll see you next week with Laurie Rousseau. Help me.
Nepton.
Very good.
Oh, and Brian's posted a comet sighting opportunity.
Yes.
Oh,
okay.
Goodness.
Another 2 weeks, it'll be in Draco, somewhere between Ursa Major and Ursa Minor.
What magnitude?
5th.
Oh, getting there.
Might actually see that one.
You got to get up in the middle of the night.
CO22E3.
Yeah, it's an early morning comet. It's one of those things that I had a look at it, and it's kind of like a 3 o'clock, 4 o'clock kind of thing, if you're into that.
And the moon's up right now.
Yeah.
Right.
There's also a conjunction coming up as well. I think there's a Venus Saturn conjunction coming up.
Oh, it's supposed to be good. That's right.
1 degree, I think, or something like that. So that's always kind of pretty. There's a third item, and I can't remember what it is. There's another thing going on either this month or early February. I just can't remember it right now.
Rain?
Okay, everybody.
Rain?
Bye-bye.
Rain. All right. Good night.